In example 3, the idea is that you see how we can have we can do implicit differentiation even with the new functions that we have learned the derivative of, the trig functions. So just pay attention that this is a composition of two functions. You have the sign of and inside you have x plus y, and then in here we have the product, so we're going to be using product rule as well. So I'm finding y prime. Derivative of the outer function will be cosine evaluated at the inner function times the derivative of the inner function. Now the inner function is a sum, so derivative of x will be 1, and then derivative of y will be also 1 times the derivative of y in respect to x, which is y prime. Now the derivative of the right side, we have the product of two functions, so the product of the first function 2y y prime times the second function, sorry about that, the struggles of living in the city, plus the first function times the derivative of the second function, y squared times negative sine of x. And I just have to solve for y prime, which happens to be present on both sides of the equal sign. And that's probably the only thing that makes this problem inconvenient, but I don't think it's particularly difficult. I will distribute cosine of x plus y plus y prime cosine of x plus y. Remember that x plus y is under the cosine function, so I will never dare to distribute y prime over x plus y because they are inside the cosine function, so please don't even think about that. 2y cosine of x times y prime minus sine of x. Well, I'd rather put y squared sine of x so that it doesn't look like it's sine of xy squared. Okay, so now I'd rather have the y primes on the left side, but it's just preference, it really doesn't matter. But if I do that, then I'm going to have this brought to the other side as a negative, so I'm going to have two negatives. So I just want to keep it as positive as possible, otherwise I'm going to have to factor out a negative, and it will add one more step to my calculations. So I'm going to bring this here and then this term over here. So I have cosine of x plus y squared sine of x equals 2y cosine of x times y prime minus y prime cosine of x plus y. In here I'm going to factor out the y prime, so I have y prime 2y cosine of x minus cosine of x plus y equals the left side. Nothing has happened and nothing will happen. I have nothing to simplify here, and then I want to divide both sides by this expression, so I just have y prime equals cosine of x plus y squared sine of x, and everything divided by the quantity 2y cosine of x minus cosine of x plus y. Again, what does this mean? This is the derivative of this function, for which I don't even know the shape of, but I know that the tangent line will have a slope based on x and y coordinates of whatever point I'm evaluating. So implicit differentiation is just another way of taking the derivative. So therefore it's possible for me to take the second derivative if I wanted to. Now this may remind you of the equation of a circle, x squared plus y squared equals 16, that will have radius 4. But because the degree is higher, this is not a circle, but it kind of looks like a square with soft corners. And this is actually known as the fat circle, but I think it will be politically incorrect to call it that, so let's just call it the full figure circle. Look how happy it is. Doesn't get to be called that. Anyhow, I can find the second derivative of this, so I'm just going to take the derivative with respect to x for all of them. You can use either notation. It is fine. Derivative of 16 with respect to x. This expression depends on x, so I'm just taking the derivative as usual for x cubed. This expression does depend on x, so that requires me to do the chain rule. So I'm just going to take the derivative of y to the 4th power, which is 4y cubed, times derivative of y with respect to x, which is y prime. And this is a constant with respect to x, so that's 0. I can divide the entire equation by 4. So x cubed plus y cubed y prime equals 0 divided by 4, which is 0. And then solve for y prime, and that will be negative x cubed over y cubed. I'm going to subtract both sides by x cubed, and then I'm going to divide by y cubed both sides, and that's how I get this. So that's the first derivative, and now I'm going to take the second derivative, which will imply that I'm going to take the derivative of this again. So y double prime is, I have a quotient here, so I'm going to apply the quotient rule. Not only I have the quotient rule, but also this is a function of y, so I'm going to do the chain rule as well. So let's get ready. Derivative of the top, which is negative 3x squared, times the bottom, minus derivative of the bottom, which is 3y squared y prime. Remember chain rule, I'm taking the derivative of the inside, times the top, everything divided by the bottom square. And that's the quotient rule. And now I'm just going to simplify. This becomes negative 3x squared y cubed plus 3y squared y prime. Where is it? I made a mistake somewhere. This is the derivative of this one times the top. Let me see. So paranoid. No, everything is fine. Okay. Y prime x cubed over y to the 6. Now the only, and this is correct, and this is mathematically correct, and depending on the kind of problem that you're facing, if you have to find the second derivative at the point I don't know, 3, 4, this is an example, this is not part of the problem in the book, but if you have to find the derivative, the second derivative at this point, you will have to find the first derivative at that point, because that's the information that you need. The second derivative is something based on the x and the y coordinate of the point, and also the derivative at that point. So this is mathematically correct, and it could end here. However, there is a very nice simplified version of the second derivative, so you won't have to keep going. If this was a multiple choice, definitely you will see this answer, then that's it, like there is no other way to go. But I would recommend to go the extra step, just because it looks a lot friendlier, and also it sharpens our algebraic skills. So I'm going to replace y prime with this expression that I had found previously. So I have negative 3x squared y cubed plus 3y squared negative x cubed y cubed times x cubed, and everything is still divided by y to the 6th power. Now I'm going to simplify the y squared with y squared here, so I'm going to have a y in the bottom. So I have negative 3x squared y cubed plus well, minus with this negative here, 3x to the 6 over y, and everything over y to the 6th power. Now I notice that I have a fraction here and a fraction here. So as I mentioned before, you are welcome to write this as 1 over y to the 6th power. However, if I multiply this fraction by y, top and bottom, the way I simplify it will be a lot easier. Check this out. So if I multiply the top by y, then this one is going to have an extra y, negative 3x squared y to the 4th. And then this y times this expression will cancel out the denominator here. So I'm going to have minus 3x to the 6th, and everything divided by, if I'm doing this on the top, I have to do it on the bottom so that I don't change the value of it. So now there is no this fraction of a fraction anymore. I only have simply one fraction. Now I'm going to factor out everything that I can on this expression. The negative 3, they have it in common, and also an x squared. So I meant to make a parenthesis, but I'm going to change it to an x squared because that's also something that they have in common. So on the first term, the only thing that I have is y to the 4th, and then on the second term I have an x to the 4th. Now let me see if I did it correctly. If I distribute, I'm going to have this back, so I did. Yay. Over y to the 7th. Now this, from the very first equation, I know that equals 16. That was the function that we started with, the full figure circle. So I'm going to replace that, and I have negative 3x squared times 16 over y to the 7th, and that gives me negative 48 x squared over y to the 7th, and that will be my second derivative, nice and cute.